Good afternoon. I welcome you to the session of experimental methods in fluid mechanics, and we will continue our discussion on flow measurements, and we have discussed this aspect in my last lecture that we can measure flow velocity using another important instrument, that is thermal anemometry. And if we try to recall that flow measurements, it may be the measurement of flow rate, volumetric flow rate, mass flow rate, or it may be the measurement of point velocity, or it is determination of the flow streamlines. Now we have discussed that thermal anemometry, which is used to measure the point velocity measurement. So we have discussed about that thermal anemometry. This thermal anemometry basically is the thermal anemometer that which is used to measure velocity using heat transfer, and of course I can say is measure velocity by heat transfer using either hot wire or hot film. So this thermal anemometry is used to measure velocity of velocity by heat transfer using hot wire or hot film, and we have discussed that hot film, hot wire is basically a metal wire of diameter is 1/10 diameter of the human hair, and hot film is again a metal film, a very thin film, which is metal film on a glass. And this wire or film, when we talk about, these are basically electrically heated element which are electrically heated and placed in a flow field, and by measuring the heat transfer we can measure the flow velocity. And in fact we have seen that the heat transfer, that is essentially heat transfer that is I square r, and this I square r, which is I have told that that is experimentally and analysis and experimental evidence indicate that this is A plus B under root u, where A and B are the constant, and these constants are determined using experimental data. And so knowing the value I square r, that is heat transfer, we can calculate the velocity. And we have discussed the hot wire thermal anemometer, and we have seen that hot wire thermal anemometer is used to measure flow velocity, I can say component of flow velocity normal to wire. So we have schematically described that in fact the different dimensions of hot wire thermal anemometer, and we have seen that this hot wire thermometer is used to measure component of flow velocity which is normal to the wire, but it is not the case that always we can always the measurement will be the correct one, because the heat transfer. So the component of flow velocity which is parallel to the hot air is also responsible to take a I mean the heat transfer that we have measured, that also includes the component of flow velocity that is parallel to the hot air. That means what I can say, that the heat transfer that is also affected, the heat transfer that is also affected by the component of flow velocity that is parallel to the air, but that we to if you would like to include that, but we have discussed that effect is not very high and that can be included. But the question is, if really the component of flow velocity which is parallel to the air is very high, I mean that may be the case for the turbulent flow where the flow velocity is highly chaotic in nature, then the hot air anemometer that we have discussed in the last class may not work. So that means the hot air anemometer that we have discussed in the last class, that the normal component of flow velocity, which is I mean the component of flow velocity, the heat transfer is that will be affected by the component which is parallel to the air, but that component is not significant when we talk about very the flow is not turbulent, and the measured value of flow velocity may not be the wrong. So I can say if the flow field is highly chaotic, highly turbulent, then the component of flow velocity will be there, and the existence of the component of flow velocity which is parallel to the air will also affect the heat transfer, and for that the simple type hot air that we have discussed schematically, those hot airs may not work. Now question is, that means if we want to measure two velocity components, that means if we want to measure two velocity components, so it is not always the case that we will have only one component of velocity. So if you would like to measure two velocity components, then hot air, I can say, I mean the design of hot air will be different, and I can say we can use two wires at right angles to each other to measure the velocity components. So the schematic depiction we have seen in the last lecture, where we had only one hot air, and that using that hot air anemometer we can definitely measure the velocity component which is normal to the air, but by measuring the heat transfer. But we also need to know that the existence of velocity component which is parallel to the wire will affect the heat transfer, and if you would like to really measure the velocity components, I mean two components, then we need to modify the design of hot air, and one such modification is that we can use two wires at right angles to each other to measure these components. So now we will try to see the schematic depiction of the hot air, where two wires are used and two wires are placed right angles to each other to measure the components. So now we will try to use that hot air having two wires. So, we will now see the schematic depiction of the hot wire. So, now I will try to draw that this length is 30 mm. Just I am showing the different dimensions, and this is 2.3 mm diameter, and now we have two different wire. And these wires are placed right angle to each other. So, this is hot wire having two wires, and these two wires are at right angle to each other. Now, a few important things that we should note, that this hot wire responds to rather I can say hot wire only responds, I can write these things, that hot wire only responds to change in to the magnitude of the velocity, I can say, to the magnitude of velocity. So, we have discussed about hot wires. Now, hot wire means we have seen that only single wire, and then we have seen that if the if we need to place this hot wire anemometer to measure flow velocity in a flow field where the flow field is highly chaotic, then the measurement may not be the correct one. But when the if we consider that the disturbance, rather I can say the heat transfer measurement which will be affected by the component which is parallel to the wire, if it is very less, then we can measure the velocity component, but it may not be the case always, that I said many times. So, we need to modify the design, and this is the schematic where you can see that two wires are this hot wire anemometer is having two wires which are placed right angle to each other. Now, a few important things that we need to note, that hot wire only responds to the magnitude of velocity, but very important thing that if we need to really know whether the reversal of flow velocity is there, and that the hot wire cannot cannot be used at all. So, if we need to measure only the magnitude of the flow velocity, then this instrument can be used, but if we need to know the flow reversal, then that means a directional change of the flow. So, that means I can say if we need to measure directional change, that is flow reversal. The hot wire can be used. Another thing, so these are the important things we should note. This hot wire we can use to measure point velocity. This responds only to the magnitude of velocity. If we need to know the directional change of the flow velocity component, that is the flow reversal is there, this hot wire cannot be used. And also the free convection effect, the free convection imposes a lower limit on the velocity that can be measured. So, the free convection also limits, rather imposes a lower limit on the velocity that can be measured, I mean velocity that can be measured. So, these are the important points we should note, at least when we are discussing about the thermal anemometer. This is one of the most important instruments which is used to measure point velocity, that we will discuss again today. And we have discussed about the geometrical shape and of defined hot wire. Hot wire is having only one wire, that is single wire, and we have seen the limitation of the hot wire anemometer when it is having only one wire, because at that time, because mostly rather I can say not mostly, this instrument is used to measure flow velocity by heat transfer. So, the heat transfer that will be there because of the other component, I mean it is not the fact that always there will be heat transfer because of the normal component of flow velocity. So, if we really need to measure the velocity components in a flow field, and that is more practical in different situations. So, in that case we need to modify the design, that in that case we need to have at least two wires, and wires will be placed at right angle to each other, and we can measure components of velocity. But while we have discussed this hot wire technique which is used to measure, we also should discuss the limitations of these limitations which are there, rather which are associated with these instruments to measure the flow velocity components. That is, hot wire can only used, rather this wire only responds the change in rather magnitude of flow velocity, but the change in direction, that is flow reversal, cannot be measured. And of course, free convection, that will be there, that cannot be eliminated. There will be always a free convection effect. So, that effect imposes limits on the lower velocities that can be measured. Now, we have discussed about the hot wire. In fact, we have discussed about straight general purpose hot wire probe. I mean we have shown its different dimensions, and we have discussed about the case where we need to have we have only one wire we can measure. We have also discussed that the requirement of two different wires, because the flow field may not be always I mean there will be, it is not, I mean flow field may not be always very laminar where only a single component will be there. If it is highly laminar, then the flow field which is there parallel to the wire, that will definitely affect the heat transfer, but we can ignore because of its magnitude. But this won't be the case for the chaotic flow scenarios. So, in those cases we need to modify the design that we have seen, but we should know that this hot wire thermal anemometer, this can be operated based on two modes. So, this can be operated in one of the two modes, I can say, right, in one of the two modes. One is constant current mode, number 2 is constant temperature mode. So, this instrument can be operated in one of these two modes, either constant current or constant temperature mode. Now, if we, but at least we should know that what is happening in constant current mode. So, if we now talk about constant current mode, so constant current mode, in this mode again I am telling one hot very thin wire is there. So, these wires are heated electrically by passing current through them, and then this instrument is placed in a flow field. So, when the fluid is approaching that current, there will be heat transfer, and that heat transfer that we have seen analytically and experimentally evidence indicate that is nothing but I square R, that is a heat transfer, and that is A plus B root U. A and B are constant, that is obtained experimentally. So, knowing the heat transfer, now we can calculate the flow velocity component by since A and B are known. So, in constant current mode, what is done, a fixed current is passed through the wire, and voltage across the wire indicates the heat transfer rate. So, our objective is to know the heat transfer rate I square R. Now, knowing this heat transfer rate, we can obtain the flow velocity component. I mean, whether it is if only one component is there, but if it is kind of chaotic flow, then there will be multiple components. But again, we have seen that two wires can be placed right angle to each other to measure the normal component as well as the lateral component. But in the constant current mode, what is done, a fixed current is passed through the wire, and voltage across the wire is that is an indication of the heat transfer rate. Now, this constant current mode that was developed initially. So, I can say that this was developed, I mean initially, and this was the original mode of operation. So, the hot air thermal anemometer, when it was developed on the basis rather that it can be operated using constant current mode. That means a fixed current is passed through the wire, and the voltage across the wire is measured, and which is nothing but the indication of the heat transfer rate. So, this was the original mode of operation of the hot air and thermal anemometer. But I can say that later when stable when stable feedback circuits were available, then the constant temperature mode, that is another mode, the constant temperature mode was developed. So, when the stable feedback circuits were available, then constant temperature mode was developed, and again we need to know what is new in this mode, and if we follow this mode to measure the flow velocity using hot air, then what is done. So, the hot air operated using constant temperature mode, and in this mode, the resistance, that is the air temperature, is held constant. So, constant temperature, resistance of the air is held constant. So, and the voltage rather by how? By placing the probe in one arm of a Wheatstone bridge that we have studied in our class 2 level physics. And so, the objective is to maintain a constant temperature of the air. By how? By placing the probe in one arm of a Wheatstone bridge, and the detector current, rather I can say where detector current is the input to an amplifier that supplies the bridge voltage. We will now try to see it schematically, but so this is different from the constant current, where we have fixed current is passed through the wire, and that is what we have discussed in the last slide, that a fixed current is passed through the wire and voltage across the wire is measured, and that is the indication of the heat transfer rate. But in this mode, the resistance or temperature of the wire is held constant. By how? We can make the temperature, or rather we can consider, or we can maintain the resistance of the wire is constant by placing the probe in one arm of the Wheatstone bridge, where a detector current is the input to an amplifier that supplies the bridge voltage. So, now if we try to look at, rather if we try to see the schematic depiction of the constant current hot air anemometer, it will looks like this. So, so there is no any, so this is hot air, and So, this is placed in one arm of the Wheatstone bridge, I am not going to explain because we have studied this in class 2 level, 10 plus 2 level we have studied this. But at least I am trying to draw the schematic. And say this is R2, this is R3, this is RS, this is R1 and this is R4. Now, this is hot wire and this is the flow velocity U and this is insulated probe. So, there should not be any heat loss, insulated probe. And these 2 points, as I said that these 2 points and that is potentiometer. So, this is potentiometer. So, this is a schematic of the hot wire anemometer circuit. Now, as I said that here the temperature of the wire is maintained constant by placing it in one side of the Wheatstone bridge and next is the detector current is the input to an amplifier. So, a detector current is an input to the amplifier and that supplied the bridge voltage. Now, so using now again by measuring the heat transfer we can calculate the flow velocity, but again the design will be modified if you really would like to measure, I mean if you would like to measure the 2 components, in that case we need to have 2 wires which will be placed right angle to each other, and the design geometrical shape of the hot wire, whether you are like to interested to measure velocity components, in that case we need to have 2 wires, but if we ignore that that means that the heat transfer that will be affected by the existence of the lateral component of velocity and that is really small. I mean if we can ignore if the flow field is highly laminar, in that case that aspect can be ignored. In that case this is the actual schematic to measure the flow velocity, of course point flow velocity, and here we are maintaining the temperature constant and we are placing this probe in one arm of the Wheatstone bridge. Now, again another of few important aspects that we need to know that small thermal mass of the air. So, I can say due to small thermal mass of the wire the heat transfer adjust almost, I can say, instantaneously. To change in the velocity, flow velocity. So, due to the small thermal mass is not very high, so that effect due to the inertia, that is inertial effect, is not there. That means this is very sensitive instrument, that is what I would like to convey, that the thermal mass of the element is very small. So, the moment when the flow velocity, that the component of velocity is there, so heat transfer will adjust instantaneously to change in the velocity. So, with the change in velocity component, the heat transfer that will be there, that will change itself, that the heat transfer will adjust so fast that we can measure accurately. That means that effect of inertia, the lagging, that aspect should not be there. So, the flow velocity, when the wire, we are placing wire in a flow field, so velocity is there, but it is not the case that we can measure the heat transfer after some time, because that effect is not there. So, the inertial effect because of the thermal mass, that is not there due to the very small amount of thermal mass, very thin film, thin wire. So, that aspect is not there, and because of this is one of the most important, rather I can say very accurate, it is used to measure velocity component accurately. And not only that, because of this I can say that it is so fast that a 5 micron diameter uncompensated wire will respond well to 1 kilohertz velocity fluctuation. So, only a 5 micron diameter uncompensated wire will respond well to 1 kilohertz velocity fluctuation, but if we try to compensate it again, now I will write it, that if we try to compensate, that means, and not only 100, and this also I can say that this can be used to, rather up to about 100 kilohertz depending upon the fluid velocity. Depending upon the flow velocity, using a compensation circuit. So, the response is very fast, that is what I would like to convey over here, that this wire can still be used up to the 100 kilohertz depending upon the flow velocity using a compensation circuit. So, these aspects, so I can say these aspects makes the hot wire anemometer ideal for measuring the rapid fluctuation of velocity, I can say flow velocity in turbulent flows. So, this is one of the important point that it can, thermal mass is negligibly small, and because of this a 5 micron uncompensated wire can, that is what I have written, will respond well up to 1 kilohertz velocity fluctuation, but this still can be used up to the 100 kilohertz depending upon the fluid velocity components using a compensation circuit. And this feature, I can say this important feature makes the hot wire anemometer ideal for measuring rapid fluctuation that is there in a highly chaotic flow environment, that is in the turbulent flow. But we have discussed many important points. We have discussed the design I can say we have discussed the operational principle of the hot air anemometer. We have discussed about their modes of operation. We can use either in constant current or constant temperature mode, and we have seen that if we really need to measure the velocity components which are there, that is a normal component and the lateral component, then we need to have slight modification in the design, that we need to have two wires which are right angle to each other. Then also we have seen that these wires are can respond well with a change with the magnitude of flow velocity, but if we need to really measure the directional change, that is the reversal precisely, I can tell, and that cannot be used. And then we have discussed that this, because of the very small thermal mass, the inertial effect can be ignored, and this heat transfer adjusts so instantaneously with the flow velocity that even a 5 micrometer diameter uncompensated wire can respond well up to the 1 kilohertz velocity fluctuation. And if we need to use it for even for a larger fluctuation, that can be used using a compensation circuit. And because of this advantageous features, the hot air anemometer is much more suitable to have a flow velocity measurement in a chaotic flow environment, that is in the turbulent flow. So we have discussed so many points, but finally we need to know that there are a few complications, rather I can say there are many complications that have to be considered while we are using this instrument to measure the flow velocity. So in practice there are, I can say, many complications. And we should know those, at least if we know them, then when we are using this instrument, rather hot air or hot film anemometer in a flow field, we should take precaution. So there are many complications, and those complications we need to consider. So we need to consider those. Number one is temperature and humidity fluctuation. In the flow. So if we need to measure flow velocity component in a flow field where temperature and humidity will fluctuate, if the temperature and humidity fluctuates, then we'll face difficulty to measure flow velocity. And because temperature change, if that is there, then because we are measuring flow velocity by measuring the heat transfer, so if the temperature is change of the fluid, then it will be very difficult. Number two is very important, that the thermal interactions between the wire and solid surface. So that means if we go back to the schematic, we can see the small wire is connected between two ends. So the wire is connected with the solid surface. So the thermal interaction we cannot stop. The thermal mass is very small, but we cannot really ignore the thermal interaction between the wire and the solid wall, and that interaction may not give us the correct, if that interaction is still there, that might leads to error and complication in the measurement procedure. And finally that is the turbulent intensity. Turbulent intensity. That means as I said that this instrument is really suitable to measure flow velocity component, other flow velocity in a turbulent flow environment. So depending upon the intensity of the turbulent flow, there will be different issues like dissipative effect and so many other things, and those effects if we need to consider, then I mean these are the complications I can say. I mean those issues cannot be considered while we are measuring this measuring flow velocity using these components. But at least what I can say that the large amount of, I can say, research, this is not only the theory, but large amount of research on understanding the physics of the hot air anemometer have made this instrument much more popular, much more reliable instrument in measuring the flow velocity. So when we talk about the thermal anemometer, it is not the case that relying on the theory you are telling that this instrument is suitable to measure flow velocity components even for the turbulent flow field, but a large amount of research that has been done. So I mean I can say large amount of research on the understanding of the physics of the thermal anemometer, that is very important, have made this instrument much more reliable, much more popular in measuring the flow velocity components in the other flow velocity in the in different flow fields, right, laminar and turbulent. And I can say that we have started our discussion to measure the flow measurements. In fact, we have started our discussion using the flow obstruction flow rate measurement, and then flow measurement using the drag. So those two important instruments we have discussed. Those instruments are used only to measure the flow rate, volumetric flow rate and mass flow rate. And then we have started discussion on the point velocity measurement, and I can say that the thermal anemometer is one of the most important instruments which we can use, which is more reliable, I can say, and to measure the point velocity. And if it is a laminar flow, even if it is not laminar flow, by suitably modifying the design of the thermal anemometer, it can be used to measure the velocity component even in the chaotic flow environment. So with this I stop my discussion today, and we will continue our discussion next class. Thank you.